are you talking about?
Like the TV name.
TV brand.
TV
Oh
brand.
no, I don't know where it comes from. Ah, come on. Here we go.
So Irish, like the Old English, is already difficult.
Very, very difficult.
Difficult than Old English.
More difficult. Too difficult. Alright, can you write that down? Kinetic model.
Just one question. Let's see the next one. No, I didn't pass anything. Oh, okay. See something.
Is that you, Dammy? Dammy, I'm talking to you. Is that your phone? Yeah, come on. Alright, you got that? Now, we've already talked about pressure, have we?
Yes.
Yeah, we have. Pressure, we have the formula. Do you remember it? Force over area. So we've done this definition, that's fine. And the units, do you remember? Yeah, Pascal. And we said 1 Pascal is 1 Newton per... Yeah, 1 meter square. We have all this, don't we? Right. Okay, so we'll consider our ideal gas as shown. So I don't know, maybe you've talked about this in chemistry. Have you ever heard of an ideal gas in chemistry? With your current teacher or previously? Okay. So an ideal gas, we imagine, is a gas that has a low density of colliding particles with no attraction between them, and we ignore gravity. Okay, so in the exam they sometimes ask you to give 3 properties of an ideal gas. So I've given you 4. Is a low density, colliding particles, no interaction between them, and ignoring gravity. And there's actually one more that's important. I'll just write it as 5. The collisions, no, the opposite. Collisions are elastic. Yeah, so can you write down 1 to 4 and then the number 5? Got that? And have you got number 5 as well? Collisions are elastic. Number 5? Okay, you got that? Yeah? Good. Right. So we imagine them as balls bouncing around inside of a container here. Now, okay, there's a proof I have to do with you now. The proof is very long and it's very difficult. And you're expected to know this proof for the exam. You're not expected to produce the whole proof though. You're expected to understand the proof and comment on parts of the proof that they might ask you about. So although you don't need to prove this in the exam, you still need to fully understand the whole proof. You get what I'm saying? It's a long proof, has many steps in it. We'll do it bit by bit. Okay, so before we fully look at the situation like this, with the particles inside the box, to make our life a little bit easier, we'll first just look at this situation where we have one particle and it's bouncing back and forth between two walls. Okay? And we'll call the distance between the walls L. We'll say the particle has a mass of m, and we'll say it's moving with a speed here of v, for example. And we'll just keep everything nice and simple. Everything is L, L, L. Okay. So let's look at what's happening here. This particle will collide with the wall. And what will happen to its momentum? It will change. Let's calculate the change in momentum. So delta P equals, after the collision, the particle is heading left with the same speed. So what would be its momentum after the collision? Minus mv. Minus mu. Well, what are we calling u in this one? Yeah, minus mv. So that means delta P equals minus 2mv. Okay? Now, I'll divide both sides by delta t. Like that. So, what does this become now?
Force.
Becomes force. Okay? Now, this force here is the force on the particle. What is putting the force on the particle? What is giving the force to the particle? The wall, isn't it? So, although this is minus, what I really care about is not the force of the wall on the particle, but the other way around. The force of the particle on the wall. So this is the force on the particle, but I actually want the force on the wall from the particle. Now we can use Newton's third law here. What does Newton's third law tell us? Yeah, this is from the third law of Newton. It's equal but opposite. So it's just the positive, correct. 2mv over delta t. Now, remember we have the formula pressure equals force over area. So using this formula now, but pressure equals force over area, what can I replace force by? Pressure times area. Okay? And that's equal to 2mv over delta t. Now, I'll just squish it in here. Okay. But we have our distance, speed, time triangle. Distance is 2L. It loops 2L. Sorry, can you see that okay? 2L. Speed, what's the speed? V. And the time, what we're calling delta t. So what does the time equal as a formula? Yeah. 2L over V. So the V, yeah, comes up the top, doesn't it? And what happens with the 2's? So you get mv squared over L. Now let me bring the L up to the left. So maybe somebody can tell me this. What's the area times the length? Does anyone know what that might simplify to? Very good, volume. Now, just to make it clear, it's volume, I'll write my V like this. Whereas this one here is velocity then. Okay. Now, there's still more to go, so I'll pause for a moment to let you write this much down. Wait, actually, sorry, just before you do, let me give you an example of what I mean in the exam, of a question that tests your understanding. So, for example, they could ask you, in the kinetic model, what is the cause of the force on the wall? Well, it's caused by the change in momentum of the particle colliding with the wall. Okay? Or they could ask you, what is the cause of the pressure on the wall? The pressure is caused by the force of the particle colliding with the wall. And what is the cause of the force of the particle? The change in its momentum. Do you understand? Or for example, they could ask you, what is the law that lets you calculate the force on the wall? What is Newton's third law? It will be equal and opposite to the force of the wall on the particle. Do you understand? So you need to fully understand this proof to answer a question they might have about the proof. Okay, now write it down before we continue. You have all of this? Yeah, okay. You have that? Can I scroll down? Yes, I can scroll down? Yes?
Yes.
Maybe this far?
Yeah.
Now, what does this formula kind of look like on the left? It looks a little bit, it's nearly like what? Nearly, except what's missing? Yeah, so I'll multiply both sides by a half now. And then on the left, I get the kinetic energy, wouldn't I? Yeah. But there's a little bit of a problem now. So the problem is this. The motion of the particle is just like this, left and right. Okay? Whereas really, what could its motion be? It could be all directions, couldn't it? Yeah. So there is a way to fix that, and I'll draw it here for you. So imagine you have the particle, and instead of moving left and right, it could be moving like this, bouncing around like that. So let me just draw it in this direction here, like this. Okay. Now, let me call this here x, y, z, for example, and here's its speed. We can use Pythagoras to say that the speed squared equals x squared plus y squared plus z squared. Yeah? Just it's Pythagoras basically. But there's something interesting about x, y, and z. We think that x squared, y squared, and z squared, they should all be about the same. Now, can anyone tell me why I'm thinking the x squared, y squared, and z squared should all be equal in its value, roughly? Oh, good, because you're thinking the cube shape. Not this. It's a good idea, though. Don't forget, we're talking about its speed, not its distance. If it was its distance, I would agree with you, but its speed. Can anyone think of a reason why I would think the speeds in each direction, x, y, z, should be, on average, equal? Good, that's a decent reason, because they're random. Yeah. There's another reason too, but that's fine. Say again? Not this one. I'll tell you why. Imagine that z was a bigger speed than x and y. Then the particles, on average, they would be moving up the box. If their z values are bigger, then on average you would see the particles rise to the top. What if the z was smaller than x and y? Well, you would see the particles that kind of want to start moving down. So it's kind of like what you were saying too. Because it's random, there's no preferred direction. They're all equally likely directions. It's balanced, basically. And what we have been looking at so far is just this direction, hasn't it been? Just going left and right. Okay? So this is what I called v squared here. So what you can now say is the speed squared, which is what we really need, is equal to v squared plus v squared plus v squared, which is equal to 3v squared. That's the speed squared. Yeah? So what I'll do a little trick here. I'll change this into 1 over 2 1 over 3 v squared. And what's this 3v squared now? Speed squared. So what's a half m speed squared? Now it's kinetic energy. Okay, so let me now say that's a half pv equals 1 over 3 ke. See, I told you this is a difficult proof, but don't worry, we're getting near to the end now. Okay. Now, the kinetic energy. Do these particles have any potential energy? Do they? Do they?
No, they're always
How does 1 over 3 appear?
yeah, I put that.
Oh, because I put 1 over 3 and 3. Okay, if you don't like that, I'll do it this way. A half, I multiply both sides by 3. Is that better?
Oh, yeah.
Okay, right. So then I get 3 over 2 PV equals, and then this is a half m speed squared from this little block here. So then now this becomes KE. Yeah? Now, I'll just zoom out a little bit more. This is still true if we go from one particle to n particles. The proof doesn't change. I've only been looking at one particle, right?
Yes.
But everything is still the same logic if I have 2 particles or 3 particles. So this becomes 3 over 2 PV equals total kinetic energy. Did we say there's gravity in this problem? No. So what does the potential energy equal? 0. So the total kinetic energy will be the same as the total energy. Why? Because there's no potential to consider. So then you get 3 over 2 PV equals the total energy. Now, hang on. Let me just see. Yeah, and I write it the other way around. I bring... Oh, I think that's a 3 over 2 PV. Oh, no, I do write it like this, yeah. Now look, the proof is very long. It's very difficult. But I want to explain to you why the result is actually very important. Do you think it would be easy or difficult to calculate the speed of every molecule in a gas? Easy or difficult to do? Difficult. In fact, would you say impossible? Yes. Impossible, right? So if I said to you, here's a gas, what is the total energy of the gas? You could not calculate it. Okay. However, could you calculate the volume of the gas? Could you calculate the pressure of the gas? And by simply doing P times V times 3 over 2, believe it or not, you've also calculated the total energy of all the particles in the gas. Now this is actually really significant because if you look here on the right, this is a micro calculation. It's the energy of every single particle. Too difficult to do in real life. But on the left, we call this a macro, like a big, easy to measure thing. So what we've done is we've found an easy way to measure something big and use that answer to calculate something small. Do you see why this is an important proof? Because it's like it links the big world of pressure and volume with the small world of molecules moving around. Do you understand how this connects the two worlds? The big world of pressure and volume and temperature is now linked to the small world of molecules moving around with kinetic energy. Yeah? So you can see why they have this on the course, because it links these two important areas. Yeah. Okay, so this is the end of the proof. If you can finish adding this to your notes. How far down did we finish? It was to here, wasn't it? Yeah, that was the next line. Okay. What does what mean? TKE?
Yeah.
This? It's like take. No, that's joking. TKE. T is total, K is kinetic, and E is energy. Yeah.
The speed is in 4 dimensions.
3 dimensions, X, Y, Z. Yeah.
When it is solid, the molecules like vibrate.
They still vibrate. Yeah.
Like,
Yeah.
do they all vibrate at the same energy, like at the same speed, or some might be faster, but like approximately everything is the same?
Approximately it's the same, but real life it's not. There'll be a lot of particles vibrating at the same speed, and then there'll be some that are vibrating a little faster and some a little slower.
So that means if I like leave an object on the surface for like after 50 years, it might not be on that same spot.
Yeah. Yeah. It might not even be the same mass, because there are the process where the molecules could leave the surface of the solid. You know, they vibrate off. So its mass would very, very slowly decrease. Very slowly. Yeah. Okay, do you have this proof? Yeah? You have this? I bet you haven't seen it before. Yeah, I thought so. Do you understand its importance?
Yeah.
Do you appreciate its importance?
Not yet, anyway.
Okay. Like, if we take this room, for example, I could measure the volume of it, and I could measure the pressure in the room. In fact, I think on your phone you could probably get an app to measure room pressure. I'm not sure. And from using those two numbers, I can calculate the energy of all the air molecules in total. Okay. Actually, let's just check that the units are correct. So what's the units for pressure? It's Newton per meter squared. Squared. Pressure, right?
Yeah.
And what's the units for volume?
Meters cubed.
Meters cubed. So what am I left with here?
Newton
Newton meter. And what's a Newton meter? It's a joule, which it's supposed to be. So it checks out. Yeah? Really? Yeah? It's a wow? Okay. Right, continue. Continue? So, that's our first formula. Like I said, what makes this interesting is that by knowing something easy to find, like pressure and volume, one is able to know the total kinetic energy of the molecules, which is quite amazing, I think. Okay. It may seem like we know how much work is done to a gas when we change its pressure and or volume. Bello, please. It may seem like we know how much work is done to a gas when we change its pressure and or volume, since E equals 3/2 PV. However, this tells us the stored energy in the gas and not the work done to distort the gas. I'll explain this with our second proof. So just to be really clear, what we're saying is, imagine I have my gas and it's really spread out, like it's, you know, practically infinitely big. And then I was to shrink it down into a box. And I said the box has pressure P and volume V. This energy, we can also think of this energy as the energy required to take the gas and to put it into this box at pressure P and volume V. Okay? So let's imagine I take the gas in this room, and I want to take all the gas in this room and put it into this container. I would have to use some kind of pump, wouldn't I? Some kind of machine to do that. How much energy would be needed to take this gas and to pump it into this? Well, it's that much. Okay? But that's a little bit different to this though. Let's imagine I have the gas inside a container, but then maybe I change it a little bit. Like maybe I squish it down, and this will have a new P and a new V. I want to calculate the formula for the work done to what we say distort or compress the gas. Now this would be very important in, well actually, would anyone know where would this be important? Chemistry, or I think it's a bit more mechanical.
Fire extinguisher.
Yeah, but something a bit more mechanical. So you would see this in like machines, cars, the engine, the piston. You know the piston in the car? There's a pressure and a volume, and then this moves up and down, doesn't it? And it changes the pressure and the volume inside the cylinder.
So what's the piston?
Yeah, well, this is what we'll do. We'll do a formula now. Okay, so
So like what's a piston?
what's a piston in a car? How do you not know this word? You're practically a native speaker. What? You know piston.
It's an engine.
We know piston? Yes. Guys, you know this word piston? No.
What is it?
It burns the fuel, like it heats.
Okay. I think if you don't know this word, you should check it on your dictionary. It's good to know before we continue. Aoife, do you know this word?
No.
Okay, can you check it before we continue? Do you know this?
When you native speaker that doesn't.
Hey, now be nice. Be nice.
Like this?
Yes. You know this.
It's like a compressor, right?
Yeah. Like a compressor.
It burns the fuel.
Did you check it? Do you know it?
Yeah.
Like I can see the picture.
Yeah.
Like what exactly does it do?
Compresses the gas.
Compresses the grass, yeah.
Grass or gas?
Gas.
Yeah, that's it. It compresses the grass.
Sorry. You can gas as in like the diesel or the petrol or what?
No,
Diesel and petrol is a liquid.
But what gas?
When it gets burnt.
it gets burned.
Oh,
It becomes gas.
okay. Then what happens
And
next?
it compresses like the
Now look, you can watch a YouTube video later. It's fine. Right. So let's have a look at the next proof. We have our cylinder. And what we'll do is we'll say we decrease its height a little bit. So we shrink its height by a distance d. Okay. So we would increase, we would increase the pressure, wouldn't we? And we would decrease the volume. So I want to know how much work is done here. Well, we already have a formula for work. It's force times distance, isn't it? So we imagine that there's some force pushing this down, the piston. Yeah? Now, we don't know the force, but we could know, for example, the pressure and the area. So, yeah, we again, using our formula P equals F over A, what could I change this into? F, A, and D, isn't it? Sorry, what? No, what? Sorry. P, A, and D. Okay. Now, what is AD? Volume. But please be very careful. In the diagram, what volume is it? Is it this volume or is it this volume? It's the difference, yeah, because the D is here, isn't it? So it's this volume. And how do we get this volume? It's the difference, isn't it? So that's P V1 minus V2, which we can just write as delta V. So we have this formula. The work done to compress a piston is equal to the pressure times the change in the volume. Now, just to be clear, this formula isn't 100% realistic because what happens to the pressure when we compress it? It increases, yeah. So the pressure actually changes. So what is quite often used here is the average pressure. Or we can just say that P1 is roughly equal to P2, although we really know that P2 is more than P1. But what you could use is the average if you want P1 over P2 times 2. Most people don't. Most people just say the pressure is roughly the same as at the beginning and the end. It's not though, but roughly it is. Okay, so this is a short little proof. You can write that down, please. Okay, have you got that? Yeah. Okay, let's continue. Can I continue? Right. There you go. Pressure times change in volume. Like I said, we most commonly see this in sort of machines, engineering. You know, what would you call it? Mechanical engineering, I guess. Is anybody here looking to study mechanical engineering? I know there's a lot of computers here. Any mechanical engineers? No? Maybe? Mechanical engineering? Mechanical, like with machines. Or maybe aeronautical engineering or... Which one? Yeah. That would be very important. Because for, you know, engines, pumps, machines like this, pressure and volume is extremely important topic of study. Okay. Right, continue. No. Yeah, this... Okay, so this next definition is something I think you know about already. We don't feel it, but as I'm sitting here and as you are sitting here, there's a pressure on me from above. What is that? What is pushing down on me right now? The atmosphere. Right? There's like 10 kilometers of oxygen and nitrogen and CO2, and it's pushing down on top of me right now. Now, can you guys feel it? No. No. Sometimes you can feel it if it's a little bit higher than normal. You can kind of feel it in your head sometimes. Your head might get a little bit heavy. Yeah? Sometimes. Maybe not. Maybe not. But this pressure is present all the time. And we don't feel it only because we're used to it. Do you understand? But it really is there pushing down on us. And it's actually a very big number. And it's called 1 atmosphere of pressure. 1 ATM, 1 atmosphere of pressure. And that, does anyone actually know what it's equal to in pascals? It's around about this. A little more, I think, actually. It's 101.325 kilopascals. That's a really big pressure to be on your body right now, which you don't feel because you're used to it. That's 101,000 newtons per meter squared.
So therefore, like aliens came, you won't be able to stand on a planet.
If they came from a planet with lower pressure, yes. Yeah. I think this is like this is like the idea behind Superman as well, and like other things like this, where they seem so powerful here because on their, yeah, they're used to a different environment, you know. So like for example, we're kind of used to G being 9.81. If we went to a planet where the G was smaller, then it would look like we suddenly can jump much further or fly or something like this, you know. The same goes with pressure. That pressure is quite high, you know. Alright, continue. Yeah. Oh, before I continue, this isn't constant. If we climb a mountain, would the pressure increase or decrease? Decrease. Because as you get higher in the atmosphere, there's less above you pushing down. What about if you go down into a valley? It increases again because there's more atmosphere above you. Do you understand? Also, the weather can cause it to change. If it's a sunny day, will it increase or decrease? Does anyone know? It increases. And the colder day, it decreases. Okay. And by the way, this is at sea level. Okay? Sea level. At the same level of the sea. If we climb a mountain, it decreases. And if we go below sea level, in some countries, it's below sea level, the pressure increases. What's it? Holland, isn't it? Netherlands, yeah. A lot of it is below sea level. Yeah. And isn't there some places in the Middle East as well that are below, like isn't the Dead Sea below sea level? Maybe. Anyways, there's some places on the earth that are like this. Okay, did you write that down? 1 atmosphere of pressure. Okay. That's pretty big, isn't it? This question isn't actually on the course, so I don't need to do this. We don't need to calculate what the pressure is at different heights. It's enough that you know the pressure decreases if you move up, okay? Yeah, higher altitude, like on a mountain.
Oh.
Yeah. Okay. Right, alright. Yeah. How many questions do you have for that one? Just one?
Yeah.
Nice, okay. Oh, I never got to talk about Brownian motion. I'll have to do that in the next physics class. Because one of the homework questions was about Brownian motion, which I didn't talk about yet. So, we'll do that in the next physics class. Okay? Alright, we'll leave it there.
You can call him now. Abdul Ali. Guys, call me Abdul Ali.
Call him Bello. Call him Rahman.
Oh, so I can say Rahman without Abdul.
No, you actually can't. It's not proper.
Oh, okay, you can just say that better now. I'm slapping you.
Allah,
I'll bust your brain.
It's our class until the 6 p.m. today.
See ya.
Yes, compound.
yeah?
Compound.
Yeah, it's a compound name, but that's 2 meanings.
That's 2 minutes.
Yes, Abdul is one part, Rahman is another.
Yeah, true. I didn't go as
You should have like that, me, la, la, la.
There's another names.
Yeah. All the Nigerian names for example.
The name is simple.
The name is simple.
Just go to
Spark.
Tell me, I know it's